including Hamilton later on, realized that the same equations of Newton could be reformulated in a remarkable way, not as a solution of a differential equation, but as the condition for something to be extremal, something to be minimal, yeah, or maximal. That thing is the action. So this has been an extremely fruitful idea in physics, to think of an equation as as an optimality condition, extremality condition, or some such thing. Yeah, the best or the worst or the least. Yeah. And I mean, and this has this appears elsewhere in science as well. So in any case, the point is that there is this alternative. You can formulate Newton's equation or Lagrange's equations as the conditions for the action to be extremal. And it extends also to the phase space formulation. Hamilton's canonical equations can also be formulated as a condition for a phase space action to be extremal. So these were the first reasons why the action is very important. They gave an alternative formulation. And variational principles are very important. Even if you cannot solve an equation exactly, you may be able to make a variational ansatz and put it in the action and extremize it. So that gives an alternative way of solution also. In the quantum theory, this is very, very widely used, variational approaches. Yeah. Okay. Now, another reason why action is important, or such action principles, variational principles are important, is that in the passage from classical mechanics to either statistical physics or to quantum physics, we cannot go directly from Newton's equation in any simple way. Yeah, we don't formulate quantum mechanics by quantizing Newton's equation. It is not easy to do that. On the other hand, both how it was discovered and how we discuss it today, the method of passing to the quantum theory or to the statistical theory involves the Hamiltonian, it involves the action, it involves the Lagrangian. I was just saying earlier, the amplitude of a path in the quantum theory is given by the exponential of the action of that trajectory. Yeah, it's not given by something coming out of Newton's equation directly. So the great reason to pay attention to the action is that the action paves the way to the generalization from classical to quantum or classical to statistical physics. Whereas a direct quantization of Newton's equations is not so easy to handle. Yeah, so this is why the action is very important. But you may say it's an auxiliary concept. It is not something we measure directly. To some extent, it is true. By the way, the action is also gives you an approach to study classical physics in much deeper ways, such as the Hamilton-Jacobi approach. So where we formulate the solution of a classical system as through canonical transformations, and those generator of that canonical transformation is the action. So the action is a generator of a canonical transformation, and there's an equation to determine it called the Hamilton-Jacobi equation. So that gives an alternative viewpoint to solve the classical theory, and again, it is through that route that the first passage to quantum mechanics happened. It was because Sommerfeld understood the action principle of classical mechanics well that his students and associates could find both the Hamiltonian and the Schrödinger formulation of quantum mechanics, because the Schrödinger equation is basically a quantum version of the classical Hamilton-Jacobi equation, which is an equation for the action. It is also the way where classical mechanics makes the closest approach to optics as well. Yeah, so the iconal approximation in optics is similar to the relation between wave optics and wave optics to ray optics in the iconal approximation is a lot like quantum mechanics to classical mechanics in the particle approximation. Yeah, so the action principle is very helpful in making all these connections. I mean, nature seems to like extremization principles, whether it is extremal surfaces or soap bubbles, or so these optimization problems come up very widely in science. So it's nice that we can reformulate Newton's equation also as an optimization problem.
Okay, sir. Thank you, sir. I think that answers her question. So moving on to Sanskriti.
So, sir, the next question is from Muskan Sharif of MSc first year. So, it's a question like everybody among us is thinking these days. Like, what are the current emerging areas in physics?
Okay. Yeah, I mean, there are a lot of areas. And yeah, um, so let's preface this by saying that there are interesting developments and open questions and challenges in many areas of physics. Yeah, they are not restricted to any one area. And practically any area of physics you take will have some interesting developments going on. But how will you find out? How will you find the answer to your question? Of course, you have asked me, so I have to give some answer. But if you had to find out yourself, how would you do it? One way to do it is to, well, you go look up what some of the recent Nobel Prizes have been. So that will give you an indication of some of the areas where developments have happened. Of course, it might take a while. There may be a time lag between a Nobel Prize and the development. But even aside from that, it does give you an indication of some of, I mean, not just a Nobel Prize. You can look at other prizes like various, I mean, even the Infosys Awards and the Wolf Prize, American Physical Society Awards. So all of these they serve to highlight certain areas or developments. And so that will be a good way to find out. Yeah. Another way to find out is to read some science journals, yeah, Scientific American or Resonance, or yeah, they usually have general articles on interesting areas. That will be a good way to find out. And there are also another thing. There are various lists of open problems. Right? Every so often, somebody makes up a list. Some experienced scientists, yeah, like. Around the turn of the millennium, we had a bunch of problems by the Clay Institute. You would have heard two of them are in physics. One is in hydrodynamics, the other is in quantum field theory. Yeah, but there are other such lists of open problems. So this is also an indication. Another thing comes from new technologies. Yeah, so new technologies or new theoretical tools. Both of them can facilitate development. So if there's a new technology, it will indicate that some new things are possible. Yeah. So, I mean, as far as specific areas, I'm sure you would have heard of many of the areas. I can mention a few. I'll probably miss out a lot. Yeah. So, I mean, there have been new technological or technical developments, for instance, in interferometry. Yeah. Which have improved their sensitivity tremendously over the last couple of decades. So this has opened the window into gravitational wave astronomy. Yeah. And now we can even measure neutrinos, detect neutrinos reasonably well. So neutrinos can be used as another tool to do astrophysics, in addition to particle physics. Yeah. So one talks about multi-messenger astronomy, both gravitational and gravitational wave and neutrinos, as well as light in various wavelengths, infrared, etc. Yeah. So that is certainly one area. Another area that has developed and is in quite in the news is the entire area of quantum information and quantum computing. Yeah, quantum entanglement. So here again, it is driven by two things. One, the recognition that entanglement is a very interesting topic, theoretically speaking. A lot of developments have happened there. And also on the experimental side, it's been possible to manipulate quantum systems at microscopic scales quite well. So that has brought together both technological and theoretical development. So this is another fertile area that is seeing a lot of development. There are several other things I can mention. So, I mean, there are much older problems. For instance, the behavior of fluid systems, whether plasmas or neutral fluids, they show a myriad variety of phenomena, some of which are turbulence, or if you look at plasmas, there is the open question of using controlled nuclear fusion to as a power generating mechanism, and this is called magnetic confinement fusion. So that is the subject of tokamaks, where you use magnetic fields to confine a plasma and try to have a nuclear fusion reaction, deuterium tritium. So that is another area where there is a lot of work going on. But even on the theoretical side, understanding fluid turbulence or instabilities in fluid systems is an old problem, but much of it is not solved. So there are potential developments over there too. I did mention a little bit about quantum field theory and particle physics. So there too, there are many open issues. I mean, we have the standard model, but there are at least two areas where, on the other hand, on the one hand, we have a theory, but we cannot solve the theory. We cannot predict the mass of the proton. We cannot tell many things about strongly interacting particles. So there is need for studies over there. These are challenging problems, but open problems. And on the other hand, there are experiments going on at CERN and elsewhere where we scatter particles. A lot of importance in understanding how to calculate scattering cross sections in efficient ways, and there have been lots of developments in developing more efficient ways than summing Feynman diagrams. Because there are a lot of diagrams and there are more efficient ways. So how to calculate scattering amplitudes in more efficient ways. So a lot of new developments are happening in that theoretical area. There are, if you go towards condensed matter physics, there are many things. There are quantum materials with very novel features. A lot of efforts are going in that direction. Quantum materials, phenomena like novel states of matter, high temperature superconductivity, fractional quantum Hall effects, and a whole variety of novel behaviors are being seen in strongly correlated electron systems or topological features that arise in condensed matter systems. So this is a very active area of research as well as technological developments. So that is yet another area I can mention. Another area is, you could say, the area of chaotic dynamics, both classical and quantum chaos. There are many open questions which are there, and computer simulations have really energized this area so that one can explore phenomena through computer simulations and then try to understand them in a deeper way or in a theoretical way. So the area of nonlinear dynamics, complex systems, you may hear of things like synchronization and so on. So this is another area. Of course, there is space exploration, building satellites, launching and controlling satellites. So this is very much active area where we have ISRO is also very much involved. Let's not forget other areas. I mean, I mentioned fluid turbulence, but there's another part of it, which is weather prediction or climate science. This is also extremely important area from practical point of view and from the theoretical point of view. Having a clear, good understanding of atmospheric physics and weather prediction, as you can see, will be very, very useful. It is a challenging area, or even understanding the monsoon in a better way is relevant to us. Or for that matter, climate change. So this is yet another area of active development. Climate science, if you call it that. Yeah, low temperature physics is, of course, it's been around for a long time, and it continues to be important. What happens to systems at low temperatures? So just as you want to go to high energy, you want to go to low temperatures. There are always surprises over there. Bose-Einstein condensates and condensates of other things, fermions as well. Yeah, and using those condensates as analog, as models, as way of simulating other systems. Yeah. There are a lot of theoretical models you can make up, but it turns out you can actually simulate them using atomic gases and low temperature systems. So it's very interesting from that point of view. There are other theoretical areas like the search for theories of quantum gravity and string theory. This is another area of active research. Yeah, so I mean, I'm mentioning things which come to mind, but I'm sure I've missed out others. Of course, there's the entire area of machine learning and artificial intelligence. Yeah, so that's another area where new techniques are coming up. Yeah, so you can add if you have heard of other things. Yeah.
I think.
Thank you, sir. You gave a lot of things to search about.
Nuclear physics is also very important.
I'm sorry, I did not hear what.
Nuclear physics. Nuclear physics, particularly.
Oh, of course. Yeah. Yes, nuclear physics. So, I mean, I did mention particle physics, but certainly nuclei. Every so often we hear that there are new types of nuclei, very heavy nuclei discovered, which have peculiar properties. Yes, indeed. And nuclear physics is a difficult subject. It is very difficult because it's a strongly interacting system and many body system, and it is not possible to somehow solve quantum chromodynamics and understand nuclei. That doesn't work. So you need effective models of nuclei, and there are many very interesting ideas in those areas. Yeah, so we can add that to the list. Yeah. Optics I didn't mention, perhaps I didn't, but perhaps, I mean, optics is in connection with quantum entanglement. I mean, often you use optical systems to model such things. Yeah, as well as other areas. I mean, nanoscience and nanomaterials are also very important. If you want to build a quantum computer, you need to know lithography. You need to have set up Josephson junction circuits to set up a qubit. So lithography is important in that. So yeah, so the material science is how you actually build materials. So we have to bear that in mind. Yeah.
Let's move to another question. Thank you, sir.
So there's an interesting question from Shashwat Giri of BSc third year. He asks, what exactly is vacuum? Is it really an empty space or just a relative term? Also, gravitational fields and lots of other unknown fields still work under vacuum, and this contradicts the same. Need a clear-cut clarification about complete emptiness.
Okay, so this is about the vacuum. All right, so I think maybe to start addressing this question, it is good to think about how do you create a vacuum. Yeah? So how do you create a vacuum? Well, what you do is you start by making a box and start sucking out the air from it. Yeah, you suck out the air, you suck out one of the charged particles you can find, yeah, and any other matter. If there is some dust inside, you want to remove that as well. And if there's a book inside, you want to remove that as well. Yeah, so that's how you start making a vacuum. Yeah? So that's what a vacuum is in practice. And now you can start asking about its properties. Having created what you believe to be a vacuum, what are its properties? So when I say properties, I mean, okay, you try to send a sound wave through that vacuum. Yeah, you speak on one side and ask whether you hear it from the other side. It turns out you can't hear properly, unlike in air. So sound doesn't propagate in a vacuum. Similarly, you can try to heat one side of that box and see whether you get the heat on the other side, and turns out you don't. So heat also doesn't propagate in a vacuum. So we're beginning to see some properties of the vacuum that you have just created. On the other hand, you can try to send an electromagnetic wave through the vacuum. Yeah, you can shine a light and see whether you see it on the other end through some detector or your eyes. It turns out you do see it. Yeah, so there are some things that can propagate through what you thought was a vacuum, and there are some things that cannot propagate. Yeah. So on the one hand, sound required atoms to move around, and oscillate and propagate a wave, and so also for heat you needed the random thermal motion of atoms and molecules. Whereas for the propagation of electromagnetic field, you don't need any atoms present. Yeah. Yeah. So it is empty space, but that empty space is able to support certain phenomena. Okay, so I've tried to convey a couple of things. Now we can pursue a little further. Yeah? Suppose I said you shine a light through a vacuum. Now suppose you shine a very strong electric field, very strong electric field, apply. Then it turns out that some even more remarkable things start happening. If the electric field is sufficiently strong, you can polarize the vacuum in the sense that electron-positron pairs can be produced and fly out, and then you can detect them. Okay, so a vacuum has this interesting possibility of being polarized. When I say polarized, I mean some sort of separation between charges, positive and negative, in this case particle and antiparticle, which can then be detected. So I mean, you could ask whether those particles were already present in the vacuum or whether or not. Yeah. So of course, you had tried to remove all the charged particles, so presumably they were not present. But it is the effect of this strong electric field that has produced them. Okay. So the vacuum has the possibility to germinate new particles. Yeah. So it is not a completely inert medium. So this is one additional feature that I would like to point out. Let me try to give some more points of view on the vacuum. Okay, what we believe to be the vacuum, the space around us, even if you suck out all the air and don't apply strong electric fields, it turns out that we have, in the last decade and more, we have found that vacuum has a condensate of a certain field called a scalar field. This is the so-called Higgs vacuum condensate. Throughout the space around us, there is a non-zero vacuum value of the scalar field. It is 246 GeV. It has been measured. It is there everywhere around us. We cannot wish it away. And that is very important to give masses to particles and so on. Right? So this, what we thought was a vacuum, is not completely empty. It has got this Higgs scalar field permeating throughout, but at a constant value. All right, so that is yet another feature of this vacuum. It has other features. There is something called the Casimir effect that one can look up. That is having to do with the properties of the vacuum. Let me let me take one different point of view. How to think about the vacuum? Yeah, see, when we study a quantum system, oftentimes we develop it in the second quantized framework with a many-body system. We develop some creation annihilation operators for the particles, but we start and we build up a certain Fock space, a Hilbert space for the many-body system. How do we build it? We start with the so-called Fock vacuum. That Fock vacuum is the state which is annihilated by all the annihilation operators or lowering operators. So if you want to think what is the vacuum, it is that state where there are none of those particles. Yeah, and then we create the Fock states by applying the creation operators. So this is another way to think about the vacuum in the context of quantum field theory or many-body physics. Yeah. It is the state which is annihilated by which is made to become zero by applying the annihilation operator. Let me also mention the vacuum in the context of the Dirac theory. See, in the Dirac's theory, in a simple-minded approach that he originally had, he said that we think of the vacuum as one in which all the negative energy states are filled and the positive energy states are empty. Now, this is a somewhat not very accurate way of speaking. one has to talk about it in the field theoretic context. Yeah, but roughly it is not a wrong idea. There is a sense in which then sort of the negative momentum states are all filled, and the positive ones are empty. And if you hit this vacuum, that is, you send a very strong electric field or you do other such things, then it can create an excitation of that vacuum, which may look like an electron-positron pair in the context of the Dirac theory. So, or in the Dirac language, you create a hole in the negative energy C. Yeah. So the vacuum has zero energy, but by suitably shaking it or shining a light or doing other such things, you can generate particles, and there are phenomena associated with that vacuum. So I mean, I said different things about the vacuum. I hope this sheds some light. I don't know how clear cut it is. I know the person asked about clear cut. Yeah, but these are some of the issues that one has to understand when understanding the vacuum. Yeah, a vacuum can have energy. That is in gravity. Yeah, in gravity, the vacuum can have energy. This is called, anyway, that's yet another feature. But even in quantum field theory, in particle physics, vacuum can have a scalar field present in it, a constant scalar field. This is not in dispute. This has been measured. It is very much there. Yeah.
Okay, thank you, sir. Now we'll move on to the next question, which will be asked by Vanshika.
So this will be the last question of our round. This question is about machine learning and AI, and how is it relevant in physics? Like, why do we need to do it currently in this time of physics?
Okay. Yeah, let's see. Maybe to get some perspective, let's say that, physics is a fairly mature subject in the sense that it has been around for some time. I mean, even from Newton's time, more than 1687. So, so more than 350 years or so. In the history of physics, machine learning and artificial intelligence are relatively new developments. So I would say that they join many other old and new tools which we have at our disposal, which have been developed over the years. These machine learning and AI are beginning to have some impact, though it is not very widespread yet. I mean, of course, there are certain areas where it may be more useful or more early useful at an earlier stage, especially areas where there's a lot of data which you need to sift through, or you have some sort of search problems where you have some energy surface that has got a lot of very, very nearly degenerate minima, and you need to search through all of them. Other search problems where you're searching for some optimal path among a large number of paths. And in this context, machine learning can be quite helpful. Yeah. So now physicists have also contributed to the development of machine learning. In fact, this year's Nobel Prize, Hinton and another person, Hopfield, they have used physics ideas, Boltzmann machines and such things, to develop machine learning algorithms and tools. Yeah, so physicists are contributing to machine learning. Machine learning has also been useful in physics. For instance, I did mention search problems, they've also been useful in materials physics, where we are searching for materials with specific properties. Yeah, and rather than make each of those material and check its property, it may be possible to use some kind of simulation and a way of artificially checking or simulating new materials and checking their properties. So that is another place where it has had an impact. And also in chemistry. In fact, this year's Nobel Prize in chemistry also has to do with the machine learning, artificial intelligence areas. However, I would like to also say that it's good to see what happened to other new technologies, how they were developed. This is not the only new technology. Even in our own lifetime, internet or computers have come as new technologies, and they have revolutionized science and physics. They have played an important role. Or for that matter, even earlier things like the invention of the steam engine really opened the gates to understanding thermodynamics, phase transition, critical point, critical opalescence, Tyndall effect. All these things came up because of a new technological development, namely the development of a steam engine. So similarly, I would expect that developments in machine learning will lead to new developments in physics, and conversely, they will be physics will able to improve those machine learning algorithms or ideas. However, I would also like to say that, even based on this history, it is not as though the machines are going to lead us somewhere or lead us, or we are going to be replaced by them. We have not been replaced by computers. We take the help of computers to do certain things, like have a seminar sitting in Chennai, some people in Chandigarh, or for communication and numerical simulations and all these things. But we are still deciding what the computer should do, and we are giving it its algorithm, and we are checking the output, and so we need to be very critical about that. We can of course be misled by computers. We may allow ourselves to be misled by computers, that is uncritically taking some computer output and wrongly interpreting it as the reality. So the same thing can happen in artificial intelligence, where we wrongly uncritically accept some output from some large language model as the truth, and get misled. So we need to be careful about that. We need to have checks of whatever these things are saying through order of magnitude estimates, other techniques, etc. And physical intuition. There is no replacement for that. So it's a new set of tools. And on the other hand, humans, as scientists, can try to understand why those techniques work. See, we have developed some large language model and some machine learning, but it is largely some trial and error. Something works. We don't understand very well why those methods work. And I think some effort will go into understanding why those methods work, or to what extent they can work. And of course, the exploitation is another part. We want to exploit them to solve societal problems and physics problems. So that is another thing. Just now I heard Nandan Lilekani and others saying that we should not try to develop yet another large language model. We should use the ones that are developed by to use this language, the big boys of Silicon Valley, but use it to solve some problems which are of relevance to us. So I think we should see artificial intelligence and machine learning in that context. It is not artificial intelligence. It is some kind of help that we can use machines to do for us. It is not some independent intelligence, I think. Of course, it can have bad consequences, just like anything else, which we have to guard against. I should also point that this machine learning and artificial learning can be useful in other purposes. It can be useful in the learning process, in the education process. So now you can query Google about some topic, and it is able to put together a summary of that topic, and that's very helpful. Of course, you have to check it against the sources. So it's helpful in that process. I think that is certainly a place where you and I are already using it. These chatbots and so on. They are also very useful in suggesting computer code. Yeah, if I don't know how to say write a C++ code to solve a certain problem, one can ask this large language model, and if we propose a code, we will have to just test it and calibrate it and change it. Or if you don't know Mathematica, you might ask it to give a Mathematica code to plot a certain figure in a certain coordinate system, and it will help you do that. So I think it's very useful in that way. Yeah, to do programming and such things. So sure, please learn how to use it and make use of it in whichever context, solving physics problems, learning, or improving the model itself. Yeah, so it's here to stay. Yeah.
Okay, sir. Thank you for this question. Vanshika is just disconnected because of the battery drainage of her laptop. So before starting second round of questions, that is random question round, I would like to ask you if you want a break of 2 minutes, or shall we continue with the session right now?
Okay, maybe a break of 2 minutes is a good idea, perhaps also for you. So it's now 7:23. So when does 2 minutes end?
Okay, sure.
Okay, yeah. We'll restart in a couple of minutes, 7:25 or 26. Sure. Okay.
Now, and some of our department students, Simran, Sangeet, and Dipali, will be going to ask you questions. So
Okay.
over to you guys.
So, good evening, sir. I will begin the session with the first question. This question is from Samriddhi Punj of MSc second year. It's actually maybe directly related to your work on 2 plus 1 abelian gauge theory inspired by the ideal hydrodynamics. It's a bit technical question and a bit long. So, anyways, I'll read the full question and you can answer it in parts, in whatever way you like. So, she's asking about mainly about magnetic reconnection and when does the ideal magnetohydrodynamic dynamics breaks in the region of the magnetic reconnection, and what are the variations we need to consider in that region, and what is actually happening to magnetic energy during that magnetic reconnection.
Okay. All right. Yeah. So this doesn't really have anything to do with that paper on 2+1 abelian gauge theory and ideal hydrodynamics. So this is really a question about magnetohydrodynamics.
The exact question was like, how will the gauge theory vary in that region, in that magnetic reconnection region? Like you did write gauge theory about the ideal hydrodynamics. I'm asking when the ideal hydrodynamics will break in the magnetic reconnection region. So how will the gauge fields vary in that region, and how will you make a new theory about it? Perhaps. Yeah.
Okay, I will need to think about this. Okay, so see, one thing, probably cannot do any justice to this question now. But one thing to bear in mind is that all this magnetic reconnection and so on, these things are. There's a dissipative phenomena involved. Yeah, I mean, this is not ideal MHD. This is not ideal. There is viscosity, magnetic resistivity is involved. So it would not be ideal in that sense. So some modification in that sense is involved. The other thing is that there was this reformulation that I mentioned that I had looked into that was relevant to hydrodynamics. Now there are magnetic fields as well. So I do not know precisely how or whether one can extend it to this situation. You have asked an interesting thing. I will need to think more about this before I can say anything I think meaningful or useful. So for now, I think I'm going to two main things. The model that I looked at, they didn't have magnetic fields, and two, it didn't have dissipation. Now, both of those features have to be brought in somehow or other, and how precisely to do that, I do not yet know. But an equally pertinent issue is that is it necessary to do? Is that something one wants to do, or are there better ways to look at it? Besides, that was in 2+1 dimensions. There were some special features in 2+1 dimensions which are not there in 3+1 dimensions. So those things may not extend in an easy way. Interesting question, but I don't have any clear answer now.
Okay, sir. Sir, can I contact you further through email?
Okay, sure. Yeah.
Okay.
Yeah.
Thank you, sir. Thank you.
Sure, you're welcome.
Okay, no problem. So we will move on to the next question now.
So the next question has been asked by Vanchika Ranu from MSc final year. We call a crystal anisotropic, which means a varying refractive index in each direction. This would imply a varying speed of light in different directions. So, if I go inside a crystal, would I feel as if I am in a non-inertial frame of reference?
Okay, so non-inertial frame of reference, anisotropic crystal. Okay, so let's see. Now, okay. The short answer is no. An anisotropic crystal, or for that matter, any crystal sitting at rest in the lab, is associated to an inertial frame. There is no non-inertial frame coming up in that context. Now, whether it's isotropic or anisotropic is not changing the nature of the frame of reference. So maybe I should make some other comment about this. Anisotropic simply means that the speed of light is different in different directions. Now, I'm trying to imagine why you have asked this question, but let me just recall what the principle of relativity tells us. It is the assertion, the principle of relativity as formulated by Einstein, is the statement that the speed of light in vacuum, that's the most very important point, that the speed of light in vacuum is the same for in all inertial frames or for all inertial observers, and in particular independent of direction. Yeah. So, but now, first of all, a crystal is not a vacuum, and there are atoms. The atoms there are electrons present, and when light propagates through it, it interacts with those atoms and is slowed down. Now, what you're saying is an anisotropic crystal, so it is slowed down in one direction more than in another direction. But all of that doesn't change the fact that you have not done any boost or acceleration of the frame. It is still the frame of the lab, so there is no non-inertial effect involved. This is my short answer to the question.
Thank you, sir. We will moving beyond to the next question.
Okay.
Okay, sir. So the next question is asked by Janvi Gehlawat.
Maybe, okay, just one moment. I should add one statement to my previous answer. So I said what the principle of relativity is. And the other question is, what is an inertial frame? I didn't mention what that is. So perhaps you're all familiar with it, but an inertial frame it's a frame in which isolated particles, free particles, behave in a simple way. That's what an inertial frame is. More precisely, an inertial frame is one in which isolated particles move at constant velocity. Yeah, basically in straight lines at constant speed or at rest. Yeah? So this is what an inertial frame is, and a frame fixed to a lab on the Earth is basically inertial for many purposes. There may be a crystal there, but as long as you can engineer a free particle, it will move in a straight line. But of course, because of interaction with the crystalline lattice, its path may cease to be a straight line, but that's not because the frame is non-inertial. It's because the particle is not free. It's interacting with the medium. It's interacting with the electrons and protons and nuclei in this lattice. So maybe this is what the person was asking. It's not so much that the frame is non-inertial, it's that the particle has become non-free, and that's why it's not traveling in a straight line. Okay, so that is one additional comment on that question. Please go ahead.
Okay, thank you, sir. The next question has been asked by Janvi Gehlawat. She's from master's second year. She has asked, we can decide the spin of an electron by using some external magnetic field. How can one determine the isospin of nucleons experimentally?
Okay. Okay, let's go first to the spin case. So if you have electrons, they have spin. Now, how do you use a magnetic field? The reason you can use a magnetic field is that the spin of the electron couples to the magnetic field in a manner that distinguishes the different spin projections. So the interaction in the simplest case is simply B dot mu dot B, where mu is the magnetic moment, and that's proportional to the spin angular momentum. So B dot S, if you ignore some constants, and that because of that dot product, the spin projection up and spin projection down will the magnetic interaction energy, dipole energy, will be of different signs, and for that reason the particle, the electron, will deflect preferentially in one way rather than in another. And that's how you detect its spin. For instance, in the Stern-Gerlach type of apparatus. Okay, so we can take this idea and apply it to isospin. The idea is that, so what you need is, so isospin, of course, is a certain internal property of protons, neutrons, and quarks, rather similar to spin, in fact. And the thing is that if you can find an interaction, a certain force, which will play the role of the magnetic force, which couples differently to isospin up and isospin down, then you will be able to distinguish the two. And it is possible to do that. Unfortunately, the strong interactions have an isospin symmetry. I mean, it's not unfortunate, it is a fortunate thing in another sense. So they have an isospin symmetry, at least in a simple approximation, the quarks are massless. So you cannot use strong interactions to distinguish between different isospin projections. So you cannot distinguish between proton and neutron using the strong interaction. That's why it's a symmetry of the strong interactions. However, the weak interactions do not possess this isospin symmetry. In fact, this isospin is very much a part of the weak interactions. So in particular, the up-type quarks and down-type quarks have different weak interactions through the W boson, and similarly the pions pi plus, pi minus, pi zero will have different interactions with weak currents, or proton and neutron will have different interactions with weak currents. So you can use weak interactions to experimentally distinguish between different isospin states. Let me give one very simple, very short example. I told you cannot distinguish into proton and neutron. Proton is up isospin, neutron is down isospin. However, you can distinguish with them experimentally using weak interactions, and the most famous weak interaction is the original one, beta decay. You can watch and wait for decay. The neutron will decay, whereas the proton will not decay through weak interactions. So the one that decays is the proton, is the neutron. So the weak isospin is the isospin can be distinguished using weak interactions. That is a way to do it. There are many other experimental signatures of isospin that you can use to detect isospin. I just mentioned one of them. But the reasoning is what you need to. The analogy I made with the magnetic field is now a role played by weak interactions.
Okay, sir. Thank you. Now we move on to the next question, which will be asked by Samrit.
Okay. So the next question is by Simranjit Kaur from MSc second year. She's asking that discrepancies in the standard model, we have been speculating the existence of dark matter and dark energy, but currently we don't seem to have made any breakthroughs. So she wants to know, is there any convincing evidence we are waiting for in near future, or is this just a shot in the dark?
Okay, I missed a little early part of your question, but I got the overall idea. So right. So okay. So first of all, what is dark matter? So dark matter has been proposed or postulated to explain some astrophysical anomalies. Okay, some strange things that we are seeing in astrophysics, and this is not a new thing. In fact, Fritz Zwicky, I think already about 100 years ago, was looking at the velocities of galaxies in a galaxy cluster. A cluster of galaxies, and individual galaxies move around in that cluster, and you can measure the speeds, the velocities of these galaxies, just like you measure the speed of Jupiter or Saturn or Earth in the solar system. Now, and again, the process is to use things like Kepler's laws and Newtonian gravity. Because there is a big, massive sun in the center, there is a certain speed that the Earth has. I mean, there is a certain gravitational interaction which depends on the mass of the sun. And that has its consequences for the time period of the Earth and other such things. Now, what Fritz Zwicky found is that there is some luminous matter in the galaxy cluster. You can estimate its mass. Based on that mass, that is like estimating the mass of the sun and other heavy planets. Now, based on that, you can get an estimate of the speed of a galaxy. But that speed was much, much less than the observed speed. So basically, the luminous matter, gravitating matter of galaxies is not able to explain the speed of galaxies going around the center of the galaxy. So how how is the way around this? The suggestion was that maybe there is some matter in the galaxy cluster or in the individual galaxies that is not luminous, that we cannot detect through observations of light, or maybe even neutrinos or but it is gravitating. That is, it has gravitational effect, but not luminous effect, not through electromagnetic effects. And maybe that is causing this additional attraction, additional gravitational force, which we cannot see through light emission or absorption, but will speed up the galaxies in their rotation. So this is the reason to propose dark matter, and I think this reason continues to be true, even though the discovery happened 100 years ago. The observations have not changed this picture. So dark matter is not some speculative concept. It has been proposed to answer a very specific astrophysical anomaly. What has not been understood is what this dark matter is, in the sense of what is its microscopic constitution. Is it made of it is not made of photons or protons or W bosons, because all of them interact through electromagnetic processes or weak processes, etc. It is some kind of matter that doesn't interact through usual standard model processes, perhaps, at least, or very weakly. And what it is, we still don't know. There have been suggestions that it may be some very light neutrino or some other speculative particles. So that's where we don't know. We also don't know all the properties of this dark matter. There's only so much we can measure through these processes. But some properties of the dark matter are available. We have some constraints on its properties. We don't have any direct detection of this dark matter. We are seeing it indirectly through its gravitational effects. In fact, there is one more gravitational effect which we have seen that also suggests there is dark matter, and this is in gravitational lensing. This light bending around a massive star or galaxy, and the light is bending more than it should bend if the mass that is there is what we can see. So it is as though there is some invisible mass there that is causing the light from the distant sources to bend more. And so we are left with the suggestion that maybe there is some dark matter there that is causing the bending. Again, we don't know what that dark matter is. So I think the problem has to be split into two. The gravitational effects of dark matter seem to be inescapable in their effects. They are there, but what that dark matter is, we don't know. And and the experiments are looking for it. We don't know when clarity on this matter will come. Yes, you had also asked about dark energy. That is a little bit different. That is a more recent suggestion. There may be people or some suggestions that you can somehow avoid the dark matter postulate or suggestion, but it's not clear what will replace it, or what other effect will replace it. But there are suggestions along those lines also. Now, coming to dark energy, that is much more recent. So late 20th century, I think. So where it was observed by looking at the light from supernovae explosions. I think it's a type 1A supernovae or something, that they are appearing to be much fainter than what our astrophysical models would suggest, based on Einstein gravity and our astrophysical models of supernovae. They were looking much fainter. So the resolution to this, which has been proposed, is that the universe is expanding at an accelerated rate. It is not slowing down, but accelerated expansion, and they are getting farther and farther away from each other, and that is why they are looking much more dim. So this is the suggestion, and And then it raises the question, how can the universe be flying apart at an accelerated rate when on large scales the most relevant force is gravity, and gravity is universally attractive? So how can the universe be not just expanding, but expanding at an accelerated rate? So the suggestion for that is that there is some additional energy present in the universe, which has been called dark energy, which is got some peculiar property of a repulsive gravitational interaction. It is a little bit like a fluid with a negative pressure. Positive pressure tends to compress. If you have a bottle here, the pressure of the molecules around it tend to compress the bottle. Similarly, the water inside tends to push the bottle out. This is called compressional stress. But suppose there is a string which I am pulling apart. That is called a tensional stress. It is the opposite of compressional stress. It is as though this dark energy has negative pressure. It is pulling things apart. So this is the suggestion, and of course we don't understand what it is very well again, and there are a lot of attempts to understand what it is. So I think dark energy is less well established than dark matter. But there are models for accelerated expansion, including going back to Einstein's time, cosmological constant and so on. So there are ways to have accelerated expansion. But I think the dust has not settled yet on what precisely is happening. But it is not pure speculation. There are observations that require explanation. Even more, I have just mentioned 2 or 3 things. There are more such things. One has to, the matter is still being debated and studied. And we are lacking some observational support also. More observational support is needed. Then we will be able to build better models.
Okay, sir. Now we move on to the next question.
Okay.
The next question has been asked from Megha Sharma from MSc final year. What is mass? Sometimes it is the measure of quantity of matter. Sometimes it is measure of inertia. Sometimes it is energy equivalent. Sometimes it is magnitude of coupling of field with Higgs field. What exactly is it?
Okay. So, okay, let me begin by saying, see, some phenomenon or concept in physics may come up in different places. It may come up in different places. It may come up in different eras also. 18th century, 19th century, 20th century, etc. And it may have different formulations or even different explanations or different interpretations depending on the context or depending on the theoretical framework, or whether you're dealing with a macroscopic or microscopic discussion viewpoint. So the idea of mass is one of those things. It has different facets. It has different features or viewpoints, and they add to our understanding, and this is to be welcomed. This is because we are seeing various aspects of mass through physical phenomena, so we need to understand them. Of course, it may be a bit troubling to you that, this mass is coming up here and there and having different interpretations, which one is correct, which one is wrong. It is not so much that one is right or wrong. I will try to explain why there are different viewpoints, which one may be more relevant in one context and another in a different context. Or some of them may be defined differently also. They may be defined differently and we may be casually calling them both mass. That is also possible. Then we have to be more precise. One more aspect is that the nature of physical theory is that you have some model, like Newtonian theory. Now, it explains a lot of things. It is not wrong. But maybe it doesn't explain some things. Some new model comes up, maybe relativity, and it extends the domain of validity of the phenomena that you can explain. But that relativity theory has to reduce to Newtonian mechanics in the non-relativistic context. Yeah, so it's not as though the old theory is totally overthrown and discarded. It continues to be valid in some limited regime. Yeah, so the concept of mass may change when you look at it in non-relativistic physics or relativistic physics, or in gravitational context or otherwise. So with regard to mass, it depends on the context. Maybe we can begin with Newtonian mechanics. So what is mass of a particle in Newtonian mechanics? It is a measure of inertia. What do I mean by that? It is telling us the reluctance of a particle to accelerate when you apply a force to it. In other words, a particle with twice the mass will have half the acceleration when you apply the same force. Okay, so this is the basic idea of mass in Newtonian mechanics. It is a measure of the inertia, reluctance to move, reluctance to being accelerated. Now, already in Newtonian mechanics, there is another concept of mass. So the one that I just talked about is inertial mass. Already in Newtonian mechanics, there is another concept of mass called gravitational mass, which you could have called by some other name completely. You don't have to call it mass at all. Yeah, you could have called it ants or something. Yeah, just some totally another word. And what is that? It is the strength with which objects interact gravitationally. Okay, so this is how it enters.
Gravitational
Yes.
charge, I think.
Yeah, a kind of gravitational charge, you can call it. Sure. Yeah, that's a good name. So gravitational charge instead of calling it mass. In any case, it is the parameter that enters the Newton's gravity law. Now, it is a remarkable fact that discovered originally by Galileo, that this concept of inertial mass and this gravitational charge or gravitational mass can be taken to be the same. So this is the equivalence principle. So we are beginning to see that these two concepts, a certain inertial mass and a certain gravitational charge, are actually can be identified. Of course, the gravitational one will not be relevant if you are not discussing gravitational issues. Okay, now, of course, now when you go to relativity, the concept of mass changes a little bit. In fact, energy and mass get somewhat linked. The energy of a particle depends on the frame in which it is measured, and that energy is proportional to the so-called rest mass, but there is also some gamma factor over there. So energy is related to mass in the relativistic context, but whatever this relativistic context concept of mass, in the non-relativistic approximation, it will reduce to your Newtonian inertia. Okay, so it's not that one is more correct or wrong. So I think you are aware of that. Now, there are other aspects to this issue. See, so far we have not been talking about the composition of the particle. We are just talking about a particle. But you can ask about the composition of the particle. One may try to understand this concept of mass by looking at the substructure of the particle. That is, you want to look at a composite particle, maybe a hydrogen atom. It's got some neutron, it's got some, got a proton, got an electron. You would like to understand whether that mass comes from the masses of the individual particles. Maybe it's simply the sum of the individual particle masses. That turns out not to be quite true, but one can evaluate the mass of a hydrogen atom by adding up the proton and electron rest masses and subtracting the binding energy of the hydrogen atom, 13.6 electron volts. So now we are getting a different viewpoint on what a mass of an object is, what a mass of a composite body is. It is the sum of rest masses minus whatever binding energy may be present due to their interactions. Okay, so this gives you yet another viewpoint on the mass. For instance, you can ask, where is the proton mass coming from? That is coming from the masses of the quarks, which is very small. most of the mass of the proton is coming from the interactions, from the binding energy due to gluon interactions. Yeah, so that is very different. Most of the mass of the hydrogen atom is coming from the proton mass, but most of the mass of the proton is not coming from quark masses. It is coming from gluon interactions. So this gives you a further insight. Yeah, I think you mentioned also something about Higgs field and so on. Yeah, so there it gives a different idea. Yeah, I mean, I hope you see that these are really different contexts or different questions that we are asking to give further insight. Yeah, so with regard to Higgs, the thing is that gauge symmetry is a way we describe interactions among strongly interacting particles, weak interactions, as well as electromagnetism, as well as gravity. These are all some kind of gauge theories. But gauge theories do not allow the gauge boson, the force carriers, to have a mass. That will break the gauge invariance, and that will come in the way of renormalizability and so on. But the fact of the matter is that the gauge bosons, such as W and Z bosons, are massive. That is a fact of nature. That is because the force that they transmit is very short range. Whereas if you have a massless carrier, it will have a long range force, like gravity or electromagnetism. So the question is, how can you have a gauge symmetry, but with a massive force carrier like the W boson? This problem was resolved because you cannot allow for W boson to be massive. The gauge symmetry will be broken. You cannot allow that. So we accept that W boson is massless, but it gets its mass through interaction with the Higgs condensate. I mentioned before that all around us there is 246 GeV worth of Higgs scalar field condensate, and by swimming in this condensate, the W particle is behaving as though it has a mass. That is how it gets its mass. Okay, so this is yet another viewpoint. Yeah, of course, this will not be relevant if you're talking about the mass of a tennis ball or something, talking about Higgs fields and W particles, yeah, or talking about relativity. So really, depending on the context and what problem you want to solve, you need to take that concept of mass or those issues into account.
Okay, thank you, sir. That was a very descriptive answer about what is exactly mass in different fields of physics. Okay. So, sir, actually the session has been extended so far than our expected time. So I just propose an idea to you that rest of the questions can be answered on the mail, or you provide the mail contact to yourself, or we continue further.
I mean, you're welcome to continue. I don't have a problem. I mean, if you are okay, then I am okay. Yeah.
Okay, sir. Okay, so yeah. We are continuing.
Sure.
So we will be moving on to the next question. Simran will be asking that.
Okay, so the next question is asked by Govind Krishnaswami. He's from MSc first year. He has asked, is the length contraction and time dilation real or just a mathematical artifact?
Okay, so this has to do with relativistic kinematics. Yeah. Okay, short answer is it is a real phenomenon. It is not some mathematical artifact. And how do we know, you might ask? Okay, so I mean, basically that moving clocks run slowly. Yeah, that's what time dilation is. Yeah, and okay, and moving rulers contract. Yeah. Anyway, so but okay, so and how would you know that this is a real effect? Well, there are many experimental signatures of this. One of the most famous ones is to do with muon decay. Yeah, I mean, you have cosmic ray protons coming and hitting the upper atmosphere, and in that process muons are produced, but muons are not stable particles. They decay through the weak interactions to electron and neutrinos. Yeah, so but the muon has a certain lifetime. This lifetime, when measured in the lab, muons at rest, that lifetime is some 2.2 microseconds or so. So now these muons that are showering on us from the upper atmosphere are traveling very fast, nearly the speed of light. So because the lifetime is 2.2 microseconds, you can estimate how far they will travel. Now, on average, okay, you don't know when one muon is going to decay, but if you have a large sample of muons, you will know that in the half-life, some 50% of them will on average decay. Now, what is the observation? You have a observatory at height up on top of some very tall mountain, and an observatory below that mountain, maybe under a lake or something. This was actually done, Colorado or somewhere. So what they found, they compute the flux, they measure the flux of muons at the top of the hill, measure the flux of muons at the bottom of the hill, and if the muons were decaying in 2.2 microseconds, most of them will not reach the bottom of the lake. All right. I mean, there is some particular height. It was some 1,000 meters or some number. 1,000. Yeah. Now, so there was a puzzle because they were detecting many more muons at the bottom of the hill or in the lake than was expected. Now, the explanation for this came from length contraction as well as time dilation. The point is that in the frame of the muon, it lives 2.2 microseconds on average. Okay, but the distance it has to cover is actually contracted than what we measure. In the lab frame, the height of that mountain to lake is some 1,000 meters. But in the muon's rest frame, because of length contraction, the muon says, no, this distance is actually less than 1,000 meters. And therefore, even though I will live only 2.2 microseconds, I will reach that bottom. Okay? So that is why more muons reach the bottom of the hill than you will expect from the rest frame of the muon. Same way you can analyze this from the rest frame of the lab or the mountain rest frame. In that frame, you have a moving clock. You have a moving muon. So you will the clock on the muon will run slow. Time dilation. So for the observer on the ground, it is as though the muons live on average longer than 2.2 microseconds. So a larger fraction of them will survive before decaying and reach the bottom of the lake. Okay, so you can give an explanation of this experimental observation using both length contraction and time dilation. So it's a very nice experiment. There is very strong evidence for both these phenomena. Depending on which frame you like, you can use both of these phenomena to explain it. and routinely in particle accelerators and so on, we need to account for these relativistic kinematical effects. Otherwise, the design of the accelerator will be seriously wrong. Okay.
So we will move on to the next question now.
Sure.
This question is from Anshika Vora of MSc second year. She is asking that there is a concept of particles being considered as some sort of localized fluctuations propagating in a cosmic space-time fluid. It is a bit abstract for when it is first introduced in the quantum field theory course. Can you explain it in simpler words? That what it is trying to signify?
Okay. Okay, I try to catch what you said. That you want to view particles as some kind of localized disturbance or excitation. Yeah. Okay, sure. Yeah, that's a correct idea. Yeah. I mean, and it's not a new idea from quantum field theory. This has been around for a while. Yeah. Even in water waves, yeah, there is something called a soliton, a solitary wave, which you can create in a canal with water. Yeah, I mean, there are a lot of canals from the Ganga in, yeah, even in Punjab and Haryana and all. So it's possible to create an excitation of water, which is not just some ripple or some repeating wave, but it's localized and travels without changing its shape over a long distance. Eventually, of course, dissipation will kick in. So here the field is the field of the water, the velocity field of the water, the pressure and density fields of the water, and the excitation is a localized solitary wave. This is a real thing. It was discovered originally by a Scottish engineer who was riding his horse along a canal in Scotland. Now, this idea is very robust and has been used also in particle physics. So for instance, the proton can be viewed as a solitary wave or a soliton, a localized lump of energy, density, and matter in a certain field. Now, which field? This is the pion field. Okay? So, strong interaction, the basic particles of the strong interaction are pions. Those are the lightest particles of strong interactions. And in the pion field, you can have small excitations, but you can have large excitations, which are like these solitary waves in the water, and that soliton is the nucleon. Yeah, this idea goes back to Skirm, Tony Skirm, from the mid 1950s and so on. So this idea is a correct idea, and there are very precise models that can realize not just proton and neutron as a solitary waves in a field, here the pion field, but also other nuclei. Nuclei can also be modeled as solitary waves in the pion field. And it's not only there. Even in optics, this comes up. In nonlinear optical mediums, in optical fibers, one can have optical bullets, localized energy of propagating electromagnetic fields. I mean, this is not an electromagnetic wave. That would be a plane wave that simply propagates in a manner that you are more familiar. These are localized disturbances. A plane wave is everywhere at all times. Means oscillating everywhere. But these are localized disturbances. These are called optical bullets. They are used in optical communication. So this idea is correct. It is very much around. So I mean, I forget the precise statement of the question, but I hope I have given you examples where there are concrete fields. There it was electromagnetic field. In optics, in strong interactions is the pion field. In fluid mechanics, it is the velocity and pressure fields. And as I said, there's also another field, the scalar field, that is present throughout space. You can hit it, and what you produce are Higgs particles. So Higgs particle is the longest wavelength, lightest mass excitation of the scalar field. So particles can be viewed as excitations of a field in this sense. I mean, I hope I have given some analogies through which you can understand it.
Okay, sir. Now on to the next question.
The next question has been asked by Simrandeep from first year, MSc. From the kinetic theory of gases, we know that the entropy will be zero at absolute zero temperature. But for a Fermi gas, the kinetic energy is non-zero, causing a Fermi temperature, and hence contradicting the thermodynamics that the entropy will be zero at absolute temperature. How is it resolved?
Okay, let me try to clarify this matter. So the first thing you were pointing out is what I would generally call the Nernst law, or third law of thermodynamics, which tells us that, I mean, as formulated by Max Planck, it tells us that as you approach temperature of absolute zero, the entropy of a system approaches a constant value that is independent of the pressure and volume, the manner of aggregation, and so on. Okay, so this is the statement of third law of thermodynamics, that the entropy reaches a constant value. That value we take as 0. We can take as 0. All right. So this is the third law of thermodynamics, and there is a lot of experimental support for it. Using Maxwell relations, you can, and also just the definition of specific heats, one can show that the third law of thermodynamics implies that the specific heat should approach 0 at 0 temperature, and measurements do support this observation. Not just specific heat, even coefficient of thermal expansion and tension, all these things must approach 0, and they are all these are verified in experiments. So the third law has a lot of experimental support. Now coming to the question about Fermi gas and Fermi temperature and so on. Okay, let's first understand. Okay, so see, when one talks about a Fermi gas, you are usually having an idea that this is some bunch of free fermions without any interaction. Now, that is a simple model which is nice to study, but what happens when you actually cool a system of fermions, like nitrogen, or some helium appropriate isotope, because of interactions, they tend to liquefy. A gas becomes a liquid, and at even lower temperatures, they may even become a solid. So it might not remain a gas down to absolute 0. In fact, most substances do not remain gases down to absolute 0. They liquefy. And besides, when you lower the temperature, the kinetic energy actually reduces, because at least the thermal kinetic energy, due to random thermal motions, which is proportional to kT, temperature is reducing, this kinetic energy is also reducing. So the particles do not have as high a momentum or as high as a velocity, and right. Now, I forget the precise statement of the question, but and the other thing that happens is, because the temperature is decreasing and the momentum is decreasing, the de Broglie wavelength, h by p, Planck's constant divided by momentum, is actually increasing. The thermal de Broglie wavelength is becoming larger, and therefore the particles tend to overlap insofar as their wave function is concerned. We cannot really treat them as independent, non-interacting particles. That may not be very accurate. And this is why the interactions are important. But leaving that aside, I hope you are okay with the fact that at low temperatures, it's not really a gas as it was at high temperatures. It may be different. Okay, but that aside, let me just come to this Fermi temperature business. See, what you do in, at least in the free particle approximation, or in the non-interacting approximation, let's say non-interacting approximation, is that okay, let's be a little bit specific. If you have a gas, you need it to be here, otherwise it will run away. So you have to put it in a container or confine it. So there is some trapping potential. We need to have that. Now you solve for the single particle energy levels in this potential, and usually there is some discrete spectrum of energy levels. And if you ignore interactions between the fermions, what we do following Fermi and Dirac is that we populate those levels one by one from the bottom one by respecting the Pauli principle that you can have at only 1 per state, and maybe 2 if you include spin half. So and now but the distribution depends on the temperature. But at absolute 0, what happens is that you only populate the lowest levels, only up to the so-called Fermi energy. Above that, all the levels are unoccupied, they're empty. So the Fermi distribution, Fermi-Dirac distribution at 0 temperature is actually a step function. It's a step function. Whereas at finite temperature, positive temperature, it is more smoothened out. Some electrons have been promoted beyond the Fermi energy and some below the that level. So I would like to say that at 0 temperature, there is really only one way to populate the electrons. Put them all in the lowest allowed energy levels up to the Fermi energy, and therefore the entropy is zero, there is only one way to arrange the particles. Whereas at high temperatures, there are many ways to arrange the particles for a given energy, right? I mean, you could have particles moving right, moving left, yeah, in this direction, that direction. So that's what gives rise to larger entropy in a gas. But at zero temperature, basically, you don't have all that freedom. Yeah. I mean, I've not been very precise, but I hope I have tried to clarify how things are done at zero temperature. And you brought in this thing about Fermi temperature. Now, that needs to be clarified. See, the Fermi temperature, even for a electron gas in a metal, is some very, very high temperature. It has nothing to do with the Fermi energy. It is a much higher temperature, and it has nothing to do with the ambient temperature. So that is not the correct quantity to compare with. The Fermi temperature is the temperature at which the thermal effects will be comparable to the quantum effects. But at zero temperature, it is the quantum effects that are really dominating, not the thermal effects. So it is the Fermi temperature, which even for room temperature metal is some 10,000 Kelvin or something like that, has no relevance to this issue. So at absolute zero, the entropy is zero because you basically can arrange the electrons only in one way.
Thank you, sir. Now moving on to the next and the last question of our session. To summary.
Okay, so the last question is from Swati. She's from MSc second year. She's asking that how can we understand the intrinsic parity of a particle? Is it somehow related to spatial parity or not, or is it same as the spatial parity?
Okay, so yeah, spatial parity is where the story begins, and then what is that? Well, I mean, parity has to do with reflections through the origin. So you have three-dimensional space, and you reflect a vector through the origin. So you get some reflected vector. You can, of course, reflect in a plane. It is related to reflection through the origin. So that, and now a position vector will change sign under a reflection through the origin. Same way, the velocity vector will also change sign. So these are called ordinary vectors. They are called polar vectors or true vectors. However, there are certain vectors that do not change sign when you do a reflection through the origin. The most famous of them is angular momentum vector R cross P, because both R and P reverse sign, so the product does not reverse sign. That is called a pseudo vector or axial vector. There are other examples of true vectors and axial vectors. Electric field is a true vector that basically follows from Coulomb's law and such things. Magnetic field is a pseudo vector because magnetic field, infinitesimal magnetic field, is current times dl cross r. Yeah? dl is the infinitesimal current length, and r is the position vector. So it's a cross product of two ordinary vectors. So that is actually a pseudo vector. So magnetic field is a pseudo vector, whereas electric field is a ordinary vector because it is proportional to the distance unit vector in Coulomb's law. So like this, we can classify the vectors into pseudo and axial. Similarly, scalars can also be classified into those that reverse sign under reflection and those that do not reverse sign. Using these, we can say whether a certain interaction energy, some Hamiltonian, is parity preserving or parity non-preserving. Yeah. So when you make a change R to minus R, P to minus P, V to minus V, such things, you can check whether a certain interaction Hamiltonian is respects parity or not. So by using such ideas, one can understand that the strong interactions, electromagnetic interactions, as well as gravitational interactions are parity respecting. Yeah. So these interactions respect parity. In other words, they cannot change the parity of a state. I will explain more about that in a moment. Okay. On the other hand, the weak interactions do not respect parity. That is, the interaction terms in the weak interactions do not have a definite parity. Okay. Now, so that is something about spatial parity, how parity acts. Now, so now parity is a multiplicative quantum number in the sense that if you have a system that is made of two constituent parts, maybe electron, proton, then the parity of the combined system is the product of the parities. Okay? Generally speaking, I'll say more about this, but it has this multiplicative property. Okay. All right. And of course, if you bring the systems close together, they will interact. But as long as the interactions are parity conserving, then the total system will still can be described by definite parity. Okay. So, all right. Let's see. You are asking about, okay. So now let's talk about, okay. Now, we can talk about states. See, I talked about interactions. You can talk about the interaction parity of an interaction, Hamiltonian. But one can also talk about the parity of a state. One can talk about the parity of a wave function. How is that done? Well, okay, suppose it's a two-particle system. The wave function, if it's a central force, like most forces are, then you can describe the wave function of the system in terms of spherical harmonics times some radial wave function. Now, one can ask, how does parity act in spherical coordinates? In Cartesian coordinates, I told you what it does. It takes x to minus x, y to minus y, z to minus z. In polar coordinates, you can formulate it again. It will take the polar angle to theta to pi minus theta, and it will take the azimuthal angle to phi to pi plus phi. Okay, so it has some a formulation in terms of spherical polar coordinates. Using that, you can work out the manner in which the spherical harmonics transform under parity. And the short answer is that YLM transforms to -1 to the power of L times YLM. Okay, so depending on the angular momentum quantum number L, the YLM state will have either positive or even or odd parity. S wave states will have even parity, P wave states will have odd parity. So one can talk about the parity that comes from the orbital wave function of a system. Okay, so I hope this has also been clarified a bit. Okay, so now let us talk about a composite system where you have constituents, maybe proton, neutron, or electron, proton, some composite system. Now, its parity, we will say, is from two parts. We will assign an intrinsic parity to each of the particles and also an extrinsic parity that comes from the wave function of the system. Okay, so this is where that word intrinsic is coming from. The intrinsic parity is the parity assigned to every particle in the system, which I will explain how it's done. And the extrinsic parity is the one coming from the wave function, from the manner of the system being bound together. I have explained how to get the extrinsic parity. If you have got some YLM wave function, you know how to calculate it. Now, the parity of the system as a whole is then the product of the extrinsic parity and the intrinsic parity of the individual particles. When you multiply all together, you will get some plus or minus 1. Of course, not every particle has to have definite parity, especially if there's some weak interactions involved, you cannot talk about the parity. Anyway, so let us suppose that we are discussing strong interactions or electromagnetic interactions. Yeah, then it is possible to assign an intrinsic parity to the particles. Now, how will you assign this and how will you determine it? Okay, so see, if you have a process through one of these interactions, strong or electromagnetic, then it will preserve parity because the parity commutes to the Hamiltonian. I mean, Hamiltonian is invariant under parity. So the initial state and final products should have the same parity. Initial state will have the parity given by the product of the orbital parity or extrinsic parity and the intrinsic parity. Now, in most of the atomic physics, particles are not created or destroyed, at least not electrons and nucleons, but there are particles that can be created, which are the photons. You can have photon emission or absorption. So if you have the same particles in the initial and final state, then their intrinsic parities will simply cancel out in this equation. See, the equation is saying product of intrinsic parities in the initial state times extrinsic parity of initial state is equal to product of intrinsic parities of the final products times the extrinsic parity of the wave function of the final products. But if it's the same particles in initial final state, then the intrinsic parity does not play any role. It simply cancels out on both sides, and only the extrinsic parity plays a role. However, if you have a single photon coming out in the final state in an X-ray emission, then you can measure the parity of that photon. Unfortunately, you don't have single fermions coming out in any of these processes because you only have electron-positron pairs coming out. You cannot create a single electron, at least not through electromagnetic or strong interactions. So we cannot really assign an intrinsic parity to the electron through such a process. However, through the Dirac theory, one can argue that the intrinsic parity of the electron and of the proton must be opposite to each other. This much one can get from the Dirac theory. So one can arbitrarily assign positive intrinsic parity to the electrons and negative intrinsic parity to the anti-electrons. So this is the convention. It's only a convention, but we have to choose one convention. So this is what is done. So let me describe one example of a process. This is, you consider a pionic atom. You have a pion, maybe pi minus, that is bound to, instead of a nucleus, you have a proton and neutron, basically deuteron. You have a deuteron and a pi minus. So it's a neutral system. It's a little bit like a hydrogen atom, but instead of electron, you have a pion. Okay, that thing actually decays. It decays to 2 neutrons. So you have a deuteron and a pion that decays to 2 neutrons. So you notice that in the initial state, you had 2 nucleons, proton, neutron, which have the same intrinsic parity. Final state, you have 2 neutrons, they have the same intrinsic parity. So those intrinsic parities cancel out. But in the initial state, you also had a pion, single pion. So the intrinsic parity of the pion should be related to the extrinsic parities of the initial and final states. It turns out that this pionic atom is in the spin, is in an angular momentum 0, L equal to 0 state. So the initial wave function is L equal to 0, so it doesn't have any extrinsic parity. But the final state of 2 neutrons which are flying apart, that is in an angular momentum 1 state. This can be measured. And therefore, the extrinsic parity of the final state is negative. For this reason, we can infer that the pion has to have negative intrinsic parity, and we assign that to the pion. And that is now consistent also with saying that quarks have positive parity, anti-quarks have negative parity. So if a quark-anti-quark pair is basically a pion, it will have negative parity. So that is consistent with the quark model. So it is possible to assign intrinsic parity and also measure them through such experiments. So in the same way, one can assign intrinsic parity also to photons and gluons. They are both a negative intrinsic parity, basically because photons and gluons are related to a gauge, and the vector potential is a true vector. B is equal to curl of A. B is a pseudo vector. Gradient is a true vector. So A also has to be a true vector, so that the cross product is a pseudo vector. For this reason, photons and gluons have odd parity. They reverse sign under reflection. So it's possible to assign intrinsic parities to these elementary particles, and it is consistent with the quark model assignments also. It is not very clear how to assign intrinsic parity to something like the W boson or Z boson that really interacts through weak interactions which don't preserve parity. So for that, one doesn't directly assign intrinsic parities. But certainly for quarks and leptons, we assign positive intrinsic parity. And you can work out also the parity of, I said the pion is negative parity, so we call it a pseudo-scalar meson. You may have heard this. Pions are pseudo-scalar mesons. Whereas rho meson is a vector meson. So that is, that also has negative intrinsic parity. So this is a brief discussion of what intrinsic parity is. And I have made the distinction between extrinsic and intrinsic. Extrinsic is accruing from orbital wave function, whereas intrinsic is for that particle considered as a single unit. Okay, so that is a brief discussion of parity in this context.
Okay, thank you, sir. That was indeed a real discussion on parity. So now I would like to call Ekamkar Singh for a formal vote of thanks. Ekamkar, over to you.
Yes, so it was a really informative session, sir. I hope I am audible.
Yes, you are audible, Ekamkar.
Not visible.
Yeah, so
Yes.
on behalf of all the students and the Department of Physics in Panjab University, I would like to extend my gratitude to Dr. Govind Krishnaswami for taking the time out of his busy schedule to join us today and sharing his invaluable insights. We have touched many aspects of physics from, smallest in the quantum world, even to the largest in general relativity. We talked about matter and also the absence of matter, about the vacuum, from the properties of single electrons as well as to crystal of atoms and everything. So your expertise and thoughtful answers to our queries have really deepened our understanding of the subject, sir. You have actually also answered one of the go-to questions of physics students. Every physics student would like to know which current area in physics has future scope in it. So we really appreciate an answer from an expert, and really we appreciate your taking time out of your busy schedule today. I would also like to express my sincere thanks to our respected teacher, Dr. Dheeraj Shukla, for organizing this session and giving us this opportunity to interact with such a distinguished expert. So your unwavering support and dedication to our learning means a lot to us. And finally, a special thanks to the students who worked behind the scene to organize this session seamlessly. We really appreciate your efforts. Once again, thank you, Dr. Krishnaswamy, for your time and knowledge. And thank you, Dheeraj sir, for making this experience possible for us. I'm sure the session will prove really helpful for everyone, especially since our exams are right around the corner. So everyone must have just put in their doubts for the exams in this session. So yeah, thank you for joining, everyone.
Sure. So I thank you, Ekamkar, for your very kind vote of thanks. Yes, I hope this has been helpful. I must appreciate the depth of the questions and the variety of the questions that were asked. Really very nice questions. I haven't been able to answer all of them, or maybe not well as you wanted. But yeah, I know only a few things, and I shared them with you. And probably it went rather fast. I don't know. We've handled about a dozen or 2 dozen questions in a couple of hours, so it was probably pretty fast. I hope you could absorb things in such a quick time. Yeah, but I really appreciate your interest at the end of a long day. Good luck with your exams and your pursuit of physics, and as well as other things. Yeah, thanks to Dheeraj also for coordinating this.
Yeah, so really, I'm very very thankful, sir, because I was trying to interact with the students and telling that I have been fortunate to have such a great teacher, and now this is the day they signed, and they actually asked so many questions. As you told that having so many varieties and such a deep insightful questions. I'm really very much thrilled to have the answers from you, because I also had some questions, but okay, the students made it really very good. And other thing that some students are asking that would you like to send some message to them or physics pursuit? Just 2-minute message.
Just a general message about physics. Is that what you said?
Yeah.
Well, physics is fun. Physics is a very interesting subject. It requires paying attention. It requires careful thought and study, and most of all, it requires having good teachers, at least at the initial stages. That is very, very important. There is no replacement for that. Whatever AI, ML you might have, you still need some guidance of what questions to ask or what subjects to focus on. So, but my message is one of optimism. Of course, physics is not for everyone. Let's be clear about that as well. You need to have some interest, aptitude, ability, calculation abilities, skills in mathematics as well. But the thing is that physics is a very wide discipline. So what works for one student may not work for another student. It's important to find an area where you feel some connection, some ability, which you can do more easily than others can do, or something like that. If you feel that way, then you should pursue that area, or study that area more. It's not helpful if everybody pursues the same area. That will is a recipe for trouble. Yeah. On the other hand, I mean, there is no replacement for hard work but you need to study good books, and watch interesting videos that address the questions you have. So do pay attention to that. Good sources, and and I think students have an ability to detect what is a good presentation or a good explanation, because they feel they understand it better. So I think they're fully capable of doing that. I think asking questions is the first step in any of these things. So you have demonstrated that ability, certainly. Answering them is not always straightforward. And I've tried something about to do a little bit about that. But try your best in understanding things. It's not really necessary to understand all of the book of your textbook. I mean, try to understand a few things well, and that will give you a foundation to stand on. On the other hand, if you understand a lot of things very poorly, you will not be able to stand anywhere. And that will show up even in interviews or in discussions with others. See, it's okay if you say you don't know about this, or you forgot about it, or it is something you learned before and you're not familiar, or the teacher was not good, whatever. But there should be something that you understood well. And if you can show that, then that is an opportunity. People will recognize that, okay, this person has understood this thing well, and if trained, they will also understand that thing well. If you can demonstrate that, then you will be in good shape to progress further. And if you want to also be a teacher while also doing research or other things, this is really important. If you can understand one phenomenon well and explain it well, then your students will appreciate it. They'll come back to you. It's not that you have to understand all of the topics cursorily. That doesn't go very far. So, so enjoy yourself. I mean, I did mention reading good sources. I mean, for instance, even Resonance has nice articles in your spare time, or other review articles and so on. I'm sure you have people you can ask. Or make groups among yourselves and learn a subject, or prepare for exams together, try to solve problems together. I think such reinforced learning, if I may call it that. Reinforced learning is a technical term now, but reinforced by your peers can actually go a long way. So anyway, good luck with that. I hope, wish you all the best.
So many thanks, sir. So actually, I'm going through your book, and if time permits that, or I get an opportunity to teach them, so I shall be teaching those subjects, particularly those portions which you have encoded in that book, to my dear students as well.
Sure. Yes. And if you have any queries, or confusions, anything, you're welcome to ask me. Sure. I'm very glad that you are looking at the book, and I hope you find it useful.
Yes, sir.
Sure.
So many thanks, sir. So
yes.
Very good night, sir.
Okay. Have a good night.
Thank you, sir.
Okay. Bye from Chennai. Yeah.
Thank you so much, sir.
Okay. Yeah. I will leave the call now.
Yeah.
Sure. Okay.
Thank you, sir. Okay, so guys, this was really very wonderful session, and so long. I did not expect that much, but I mean, he was full of energy today, and extended his session for more than 1.5 hours, and almost try to answer all of your questions, which were really very difficult. I tell you, because I have met them. I know, who he is. And okay, so this helped you a lot, I hope so. And if it is not, I mean, some students were not actually given the opportunity to ask the question. I'm really sorry for that because we had limited time. But okay, I can entertain some of the question. Not only me, some of our friends like faculties over here, so they can entertain some of your questions at least at our own level. So those questions we are beyond our scope. We can just send to the experts. Okay, thank you very much for being with us, and this was really very nice session. See you tomorrow. Have a good night.
Good night, sir.
Thank you, sir. Good night.
Thank you, sir.
Thank you, sir. Good night.